So this is problem 76 from chapter 27. 76. So we have here a combination of magnetostatics with just statics. We have a uniform magnetic field that's into the page. So I'm going to draw it into the plane of the blackboard. This magnetic field is uniform. And here we also have a little rod that's resting on some fulcrum, some tipping point, and there's a mass that is hanging from one side, so gravity is presumably this way, and we are given that the length of this rod is d, whereas the length of this part, this little part, is just d over 4, 1/4 of it. Okay, so this is balanced. Without the magnetic field, this would not be balanced. With the magnetic field, with some current passing through this rod, it is balanced. And we are given that this m is 8 times the mass of the rod itself, and we are asked to find the current that allows this system to be in equilibrium. As you flow around the fulcrum. Okay. Now, how would we approach this problem? So there are 3 forces that needs to be balanced here. So there are 4 forces acting on this rod. There is the force because of the weight that you put on one end. There is the gravity acting on the rod itself. There is the magnetic force acting on the rod because there is some current passing through it. On top of that, there is this counterbalancing force coming from this tipping point. Okay? So these are going to cancel each other in magnitude. On top of that, the remaining 3 must lead to 0 torque around this pivot point. So how will the gravitational force on this rod would act? Well, it would act from the center of mass. So it's going to be some mg. Let me use red chalk here. So mg. This one is going to lead to some big gravitational force of 8 mg because its mass is 8 times. And on top of that, there's going to be some magnetic force, which must be, of course, you can see from this diagram directly, is equal to 7 mg. Because this is 1/4 of the distance away. This acts at the center of mass, so the distance from over here is d over 2. So distance to the fulcrum itself must be d over 4 as well. Because the distances are the same, the forces must balance out exactly. If this is mg, this is 8 mg, this must be 7 mg. Okay? So what is the magnitude of the magnetic field? That is I times d times b. This must be equal to 7 mg. So the current then is found to be 7 mg divided by dB. What about the direction? Well, the direction could be this way or that way. If it is that way, then the magnetic force is going to be this way, upwards, which is not what we want. We want the magnetic force to be downwards. If it's this way, then the magnetic force is downwards, so the current must be flowing this way. Okay? We say to the left. So the current is not a vector. You can't actually draw a coordinate system and attach some unit vectors to this, but you can always indicate the direction either by making a drawing or by writing it down.